Welcome back to the workshop. We want to continue taking a look at section 12.1, confidence intervals for one population proportion. And in this video, what we'd like to do is take a look at sample sizes required to achieve a particular error. So let's take a look at our notes. All right. So we already talked about what the margin of error looks like in our confidence interval calculations. So let's see here. What we would like to do is we'd like to take this and solve for n, so we can identify what n needs to be for a specified error, right? If we know the error that we want, we plug that in and we can find the number of observations needed for a specified confidence level as well, right? That makes sense. So let's take a really quick look at this. So the first thing I could do is I could divide by z sub alpha over 2 on both sides to get the error divided by z sub alpha over 2 is equal to this thing here, the square root of p hat times 1 minus p hat divided by n. And then, of course, I could square both sides to get rid of the square root. So I'm trying to isolate the n here, right? So I square both sides so I can further uncover the n. So I've got the error divided by z sub alpha over 2 squared is equal to p hat times 1 minus p hat divided by n. So in this case, to get n out of the denominator, I need to multiply both sides by n. So I go ahead and do that, and I find that n times the error divided by z sub alpha over 2 squared is equal to p hat times 1 minus p hat. And then, of course, if I wanted to find n itself, I just need to go ahead and divide by this thing. So that gives me, that's going to give me n is equal to p hat times 1 minus p hat divided by the error divided by z sub alpha over 2 squared. Now, is it necessary for it to look exactly like this? No, right? Remember that division by a fraction is the same as multiplying by its reciprocal. So we can also simply say that n is p hat, or the required n is p hat times 1 minus p hat times, right, the reciprocal of this would be z sub alpha over 2 divided by the error, and that would be squared still. Excellent. If you're curious about how it works with it being squared, you can recognize that the square would distribute in, and it would give you this. But rather than writing it that way, we just leave it as the square on the outside. Excellent. So this gives us n. Now there are some kind of interesting things going on here, or one specific thing that's a little bit interesting. P hat itself depends on the sample that you have taken. So you can't find p hat until you've taken the sample, but you can't take the sample until you know what p hat is because you want this desired error. So what we have to do is we have to find a way to reconcile this. So those ideas are given to us here. So if we want, let's see here, we can find it using this formula here. We'll investigate where this 1/4 comes from. So essentially, p hat times 1 minus p hat. Since we don't know p hat until we take the sample, we can't use p hat. So what do we use? We say, well, the worst that this is ever going to be, the largest this value is ever going to be, is 0.25. Or if we have a really good guess what p hat is supposed to be, right? A guess, p sub g. If you have a guess, then you can use that value. And if you have a range of values in mind, you simply choose the one that's closest to 1/2, which would be the one that's giving you the largest possible value out front there. Now, what I'd like to do to help demonstrate this is take a look at, let's see here, take a look at, you can use Desmos if I remember correctly, desmos.com. And we can go to the graphing calculator. And what I want to do is I want to find the maximum possible value that p hat times 1 minus p hat is going to be. So in this case, we're using x as our variable, so x times 1 minus x. You might notice that this is a quadratic. So if you've taken a college algebra course, even most high school algebra classes talk about quadratic functions and the vertex of a quadratic. So we can observe those things here. Now, of course, our values of proportions can only range from 0 to 1. So if we kind of zoom in here a little bit, we're just looking from 0 to 1, 0 to 1. And then if we select this, we can see the highest value it ever is when the proportion itself, right, p hat is 1/2. That's the x value here, the x coordinate, which we're saying is our p values, p hat. And then the highest that p hat times 1 minus p hat could be is 1/4, right? This is the graph of it. That's the highest point on the graph. So we know that that's the highest value. So that's fantastic. All right. So that gives us 1/4 as the worst case scenario. And then if we have a particular range of values, say we know that it's between 2 and 3/10, we just use 3/10 to get that larger value. Or if we know that it's between 6 and 8/10, then we use 6/10 because we know that that's going to give us the larger value. Okay, the larger value for p hat times 1 minus p hat, this thing here. Okay, so these are the possibilities that we use for calculating the number of samples, the number of observations in our sample required. So let's take a look at that, at an example of that. So we want to obtain a sample size that will ensure a margin of error of at most 0.02 for a confidence level of 90%. So this is saying, right, our proportions are percentages, right? 30% of the population has this characteristic. So when we say the margin of error is 0.02, right, 0.02 is 2%. So we're looking for our point estimate plus or minus 2%. Okay, 30% plus or minus 2%. So 28 to 32, that sort of thing. All right, so we want to obtain the sample size required for this. Well, we don't have a specification here of what we think the proportion might be. So we can't use a guess because we're not given a guess. We're not given a range of values, so we can't use this idea of using the thing that's closest to 1/2. We would have to use this formula here. So use n is equal to 0.25, right? 1/2 times 1/2 is 0.25 times z sub alpha over 2 divided by, not n, the desired error, squared. Now, of course, in this case, z sub alpha over 2 is z sub 0.05, which we have already discussed is 1.645. And the desired error we have specified as 0.02. Excellent. So we can plug those values in. 0.25 times 1.645 divided by 0.02 squared. And what we can do with this now, all right, is just punch it into our calculator, and that would be absolutely fine. There's no worries about that. Punch it into our calculator, and we're going to get, well, I suppose maybe do this in a couple of steps. 0.25 times, punch this portion in first, and that would be 6,765.0625. So then we multiply those, and we would get 1,691.265625. So what's the number of observations required for our sample? We're going to need, right? I can't have 2/10 or 2600ths or whatever observations. So I need to round up to the next integer. So n equal to 1,692 will give a margin of error of at most 0.02. Excellent. And that's all that we wanted to take a look at. That is the end of section 12.1. So I'll see you guys back in the workshop a little bit later for section 12.2.